to the doctoral dissertation defense of Tianyi Gu. He's a candidate in the Department of Computer Science here at the University of New Hampshire. My name is Wheeler Rummel. I'm a professor here in computer science. I've been Tianyi's dissertation advisor. My research is in heuristic search and planning. The format for today will be first Tianyi will give a talk for about 45 minutes or so, and then there'll be a chance for the audience to ask questions of the candidate. Certainly, Tianyi, I'm sure you'll be willing to take clarifying questions as we go, but if you have more substantial comments or queries, please save those for the end. Then, after the public has had a chance to query the candidate, then the public will be invited to leave, and Tianyi's committee will question him in private, and then after we've thoroughly beat him to a pulp, he'll be asked to excuse himself.
You will not do such a thing.
And then we'll deliberate upon his fate. Let me introduce Tianyi's dissertation committee. We have Professor Momtaz Begum, an assistant professor of computer science. Her work is in assistive robotics and learning from demonstration. We have Professor Laura Dietz, an assistant professor of computer science who does work in text-based machine learning and information retrieval. We have Levi Lellis, assistant professor of computing science at the University of Alberta, joining us remotely from the far reaches of Canada. His work is in heuristic search and game playing with an emphasis on techniques from machine learning and statistical estimation. And we have Professor Mark Petrick, assistant professor at UNH, who does reinforcement learning and robust optimization. Our candidate today, Tianyi Gu, holds a bachelor's and master's degree in logistics engineering from Shanghai Maritime University. Tianyi has been involved with a number of different projects during his time here at UNH. He's collaborated with an enormous number of people on all kinds of things. He's worked with, by my count, 9 other graduate students, including 3 from abroad, in universities in Germany and Israel. He's worked with 9 faculty members, including co-authoring papers with 5 faculty members at UNH. He's published in AAAI, ICHCAI, IROS, and the Journal on Disability and Rehabilitation. The work that comprises his dissertation concerns a new approach to heuristic graph search that he'll tell us about. Tianyi, the floor is yours.
Yeah, thanks, Wheeler, for the introduction. And welcome everyone to today's dissertation talk. My name is Tianyi Gu. My dissertation is about meta-reasoning for heuristic search and using uncertainty. And sorry about the technical difficulty. So without further ado, let's get started. This. How can I hide this?
No, you can move the slide.
We can move it perhaps to the bottom. Now that we know the title of your talk.
Yeah, it's better. Okay, so the central thesis of my dissertation is about, we claim heuristic search can actually benefit from representing uncertainty. For conventional heuristic search approach, we guided the search by a scalar value heuristic, right? So, and then we claim that by representing uncertainty as a belief distribution, and then if we guided the search by the belief distribution, it can help improve the performance of the algorithm, especially in some of the problem settings. We're going to show 3 problem settings in real-time heuristic search, concurrent planning and execution, and also bounded cost search. So first of all, a very brief introduction of what is heuristic search. Heuristic search is a planning approach. It tries to solve the problem. So planning is a model-based AI method. It models the environment as a state space, and then trying to find a sequence of actions that accomplishes some objects. What it does is it's model the states and actions as a vertices and edges in a graph, right? And then it models the problem. The problem becomes how you can find a path in such a graph that leading you from initial state to one of the goal state, right? And then it does this by guiding the graph search using a heuristic estimate of cost to go. So here's a small and concrete example how we can use heuristic search. For example, we want to solve this grid path-finding problem. An agent is in one of the grid cell and is trying to find a path and to a goal cell without collide with the blocking cells and the obstacles. So how can we solve this problem using heuristic search, right? So what we do is we associate costs with the states, right? So we would introduce, for example, a cost G value, which is incurred cost, meaning what's the cost to take you from the initial state to a particular current state here. So for this example, it would take like 2 steps from the initial state to this state. And then we have this heuristic value, which is essentially a lower bound on cost to go, meaning many times you can use, relax the problems, right? So you can relax problems, say, if we ignore all the obstacles, what's the, minimum steps we have to go towards the goal? For this state, it would be 1, 2, 3, like 3 steps to move toward the goal. So, and that's our heuristic estimate. And then we have this F value, which equals G plus H. So it's, 2 plus 3 equals 5 here, which is a lower bound on the total solution cost from the initial state to the goal state via this particular state. And then for a state associated with different costs, we call it a search node, which basically a vertex in the graph. And then from this node, you can evaluate the valid actions. For example, here you can go up, and then here you can also go right? So if you go up, take the go up action, it will increase your G cost from 2 to 3. There's one more step. And then you can calculate your relax the problem, like your heuristic value from there, and then you get a new F value. So you do this, so on and so forth, starting to search in this graph to find a path from the initial state to the goal state to solve the problem. Okay, then for heuristic search method, you can guide the search using these cost functions. If you guide the search, use G, it's a very well-known, Dijkstra algorithm, uniform cost search. And then if you guide the search using the H, it's a greedy search algorithm, right? You only rely on your heuristic. And then if you guide the search by a F, it's actually a very well-known A-star algorithm. It expands the nodes with the minimum F value. So A-star would guarantee to return the optimal solution path. But the problem for A-star is that it has to expand every node with F value less than C-star, the optimal solution cost. Every node with F value less than that, it has to expand that, which will take way too long for us to do this, to find an optimal solution. So what if we don't have time to do all that, right? For example, if we want to using this heuristic search technology to, for example, planning for an autonomous vehicle, and then if we are, some kids rushing to the road, and then you have to make decision in 10 milliseconds, right? You cannot afford to do this long computation. How can you apply this technology to solve that? So here's a sort of a search graph I generated during one of my internship in this company called Emotional. So as you can see here, the search graph actually can be very dense, and then the state space can be huge, right? So if you trying to search in this graph and then trying to come up with an action to not hit the kid within 10 milliseconds, it's going to be very, very challenging. Because we have this limited resource on board, right? You cannot stack zillions of CPUs in your vehicle to afford the computation. And then we have sort of the hard time bound to return the next action, right? You have to give the vehicle some command, within 10 milliseconds. You cannot leave the system out of control. How can we solve that? So then, apparently, optimal search doesn't apply here. So what's the alternative, right? So we propose like 3 problem settings which can apply to these settings. For example, real-time heuristic search, which other than the problem, it enforce a time bound, a fixed time bound to return the next action. So you have to give me the next action within, for example, 10 milliseconds. how can we do that? And then also when you're dealing with this concurrent planning and execution, we introduce the constraint that the system must be under control, right? So that's the second thing we want to introduce. And then also there's a bounded cost search, which is in the family of a suboptimal search, meaning the user can define some cost bound. Say as long as you don't hit the kit, I can allow any solutions, right? You can hit the tree or you can cross the double yellow line. I don't care. In that emergency scenario, I just care about the cost, below some threshold. I can allow that. So this is a suboptimal settings called a bounded cost search. We're gonna invent new algorithm to particularly dealing with these three problem settings. And then all the technology we're gonna introduce is under this umbrella called a meta-reasoning technology, which refers to reasoning about which reasoning to do. So if you're thinking about normal planning as thinking, right? We plan for the future, what we should do, step 1, step 2, step 3. And then meta-reasoning is essentially thinking about what type of thinking you want to do given the limited resource, right? So essentially, and then we want to avoid is, sort of overthinking, right? Never act. We want to make sure that we're not dying from this overthinking. And at some point, we should stop thinking and then starting to act, right? So we have algorithm trying to solve that. Okay, and then to apply this meta-reasoning technology, we want to use a particular category of a methodology called distributional methods, meaning we want to use distribution in our algorithm. So here's why. Because we are under time pressure, so we cannot perform offline A-star search, meaning we cannot finish our computation, right? We are in a bounded rationality. We are in the middle of the computation process. So we have uncertainties in our values. So these uncertainties, when you have uncertainty in your values, you do want to somehow using that little bit uncertainty information to guide your search. So intuitively, other than guide your search by a scalar value, distributional methods can perform better because it quantifies uncertainty, which is what search wants to resolve. So here's a troublesome example why you don't want to rely on a scalar value. For example, you have two top-level action, alpha or beta, during the search, right? And then the x-axis is the cost function, the expected cost. So the lower the better, the more on the left is the better. So in this case, you can see your best option is alpha. It has a lower cost than your second best beta option, right? So does this mean that we want to do more search in the alpha instead of in the beta? Not necessarily. But only looking at the scalar value, you might just doing that. But the problem is if you can somehow represent the uncertainty of your value. And then the agent is quite certain about the value in the alpha and quite uncertain about the value in the beta. In this case, it might be more benefit for the agent to do more search in the beta to have a better understanding of a poorly understood option, then nail down to this exact value of alpha, right? You want to see the probability that a second best option can later on actually be better and become your best option. So you want to somehow take that into account to guide your search. In this scenario, maybe you want to, by looking at the distribution, you might just do more search in the beta. So this is why we want to use distribution. And then again, we want to emphasize our claim here is heuristic search can benefit from representing uncertainty. And then we're gonna show examples how we can, by applying that idea to improve real-time search algorithm, to improve concurrent planning and execution, to improve suboptimal search. And then I will put more time in the rest of the talk on the first part, the real-time search, and then briefly talk about the rest two problem settings. All right?
Actually, one quick question.
Yes, go ahead.
Representing uncertainty, it's in the H.
Yes, so in our case, yes, we represent in H because we are solving deterministic problem here. There's no uncertainty from the nature. So it's only the uncertainty incurs from the bounded rationality because of the unfinished computation, right? Okay, so here I'm gonna move on and then to talking about the first part, the real-time search. So we modeled real-time search as a decision-making and uncertainty, and then particularly I'm gonna talking about an algorithm called the data-driven Nancy. This is a joint work with Max Leo and Job from Saarland University in Germany, and Sai and Wheeler and Mark here in UNH. So quick introduction on what is real-time search other than offline search, right? So for real-time search, the agent has to perform search for a bounded time, meaning you only search for a certain time until the time bound reaches, and then you find the best frontier node on your search frontier, and then you commit the best top level action, which will leading the agent moving towards to the search frontier, best search frontier. And then while the agent is executing that action, you reroute your search tree from the new search route here, and then doing another round of search bounded time, and then find another best frontier, and then commit the next best top level action, so on and so forth. It will interleave this search and action execution until the agent reach a goal. This is also called a receding horizon control. All right. So the conventional methods for this is called LSSR TA star, local search space learning real-time A star. It does 3 phases, which all derived from offline technology. So first of all, it has to perform the search, right? It expand the nodes with the minimum F to do the search, which is basically A star search. And then there's once the time bound is reached, it will perform this decision-making phase where you're backing up your value from the search frontier all the way to top level, and then make decision on which top level action you want to do. And then in the conventional approach, it also follows the lower bound F value to do that. It's called a mini-min backup. You're backing up your lower bound from the search frontier, and then make your decision based on that. And then there's a learning phase. You have to update your heuristic values in your local search space to prevent the agent to go back and forth in some local minima area. All right, so which is good. The agent will repeat these 3 phases until it reaches a goal. This is already proved to be complete, so the agent will eventually reach a goal, guaranteed, right? So with a consistent heuristic. But the problem is, all these are derived from offline, right? Derived from A star. And then we know that A star is optimal for offline, but the question is, does it still optimal for online planning, right? It's not, right? Because as the example I've shown you here, because of the partial knowledge of the search get, so we cannot guarantee that you follow the lower bound, or even if follow the scalar value cannot help you. You do need the distribution. And then the question is, if you have the distribution, how can you use them to guide the search, right? If the scalar value is not the answer what you want to do, how can you consider the uncertainty of your estimates? And then I want to introduce you this technology called risk-based evaluation, which trying to minimize the expected regret and given the distribution. Here's how it works. So say you are search on this route node A here, and then you have 2 top level action, alpha and beta. And alpha is your best choice for now, and then beta is your second best, right? And then to do the risk-based evaluation, you need 2 things. So one is the current belief, meaning after the search, what is the belief you have, and backing up from the search frontier. And then you also need somehow the estimate of how the belief might change with further search, right? If we do more search, what happens? So we can make assumption that if the agent doing more search, it's gonna be more certain about the value. So the distribution gonna be shrink a little bit, the variance gonna be reduced. So we can see this dashed distribution is the we call it a post-search distribution. Basically just shrink the distribution a little bit. And then you're trying to compute the risk of doing more search in each branch. Say if you want to compute the risk of doing an alpha, what you do is you take the post-search belief of alpha, which is the dashed green line, and then you take the current belief of beta, which is the solid belief, the current belief, and then you're starting to compute the loss. And again, imagine there's an x-axis here, so the value more on the left is the better, the lower cost. So we want to looking at this area, which your second best can actually be better than your current best option. So maybe roughly this area is the value of the risk, right? So people also call this a loss value, loss function in machine learning. So a loss here, and then also you do the same for the beta branch. Say you take the post-search belief of beta and then take the current belief of alpha and then compute the loss here. And then in this example, it will be this little blue area here. So then the agent will decide to do more expansion and whichever top-level action that minimize this risk value. So in this particular example, it will choose to do more expansion in the beta branch. All right? So this is all good. So if we have the belief distribution, we can use it to guide our search, right? So then the problem is where these beliefs comes from, right? How can we form this belief distribution? Essentially, we want, instead of a scalar value, now we need a belief distribution for each search node on the frontier, right? How can we get this? So in the original Nancy paper from Andrew Michel, a master student here, he proposed we can use a assumption-based, a Gaussian belief distribution, which is constructed by this, unbiased f hat of a cost value, and then also a lower bound, and then using like 2 standard deviation between these two values to construct this Gaussian belief distribution. And then what we propose here is we can actually learning this distribution from data, and then he can do online learning because there's a few parameters of the Gaussian model, and then we are learning a more expressive histogram model, so it requires offline learning. So here's how it works for the data-driven version. Is we want to learn a distribution of h star value of the optimal cost to go value given the feature of a state, and then we're using the heuristic value h and to correlate this to look up for this h star distribution. Here's how we do it. So we run a suboptimal search weighted a star on many random problems offline, and then collect all the states for each particular h value. And then we pick most common states among those states, and then starting to compute their h star value so that we can get the distribution. So actually, one thing I want to point out here is it's actually very hard to compute these optimal values for hard problem like inverse tile or even heavy tile problem. So you have to implement a very powerful optimal solver like IDA star CR to avoid the memory overload sort of thing, and then using more powerful heuristic to get this data. So anyway, here is what we get in the end is a h star distribution given a h value equal 10 in the sliding tile puzzle problem. So for h value equal 10, if your heuristic tell you you are 10 steps away from the solution, what's the actual cost that you have to do, right, for each move and for each problem instances? It's distributed from from 18 all the way to 38 somewhere here. So this is the distribution you're gonna get for the heuristic to go this distribution. Then once you have this distribution, you can somehow plug it into the Nancy framework, the risk-based look ahead to guide your search. All right. So here's another example. Before I show you one distribution, here I show you many distributions for different h values on the x-axis. And on the y-axis is the distribution. So I turn it sideways, turn the distribution sideways. You can see here, you can look at the shape of the distribution. Some of them are Gaussian-ish, but some of them are multimodal distributions, right? And actually, it looks very different from domains to domain. This is a domain-independent planning, so it's a transport and a block sort problem. And so Once you have this, you can plug that into the Nancy framework and then trying to use them to guide your search. And here's what we get. Here's results on heavy sliding tile puzzle, very challenging problem. And then since we're doing real time, right? So we are bounding the search expansions instead of the actual time limit. So we bounding say that the algorithm can only do 30 expansions. The algorithm can only do 100 expansions. The algorithm can only do 300 expansions during per iteration. And then you have to commit an action to me, right? So, and then the y-axis shows the total solution cost, the final pass the agent take all the way to the goal. So, and then compare it to the baseline algorithm offline technology LSSRTA star. So the value would be the lower the better. The more on the bottom is the better. As you can see here, both variants of Nancy can outperform the offline techniques for the very limited look ahead, right? And then DD Nancy actually performs a little better in this particular domain for 300 expansions. And here's another example in a racetrack problem, which is basically grid path finding, but you have a little bit inertia in your agent. And so it's a high dimensional state space. So here, again, DD Nancy is starting to show the power of performing a little better. Here's some planning results in more domains. So the first column is the 4 different domains we want to show, and blocks, word, transport, elevators, and we also variate the look-ahead limit, 100 look-ahead, 300, 1,000. And then the values are the mean solution cost among all the commonly solved instances. So the lower, the better. So we can see here both versions of Nancy outperform the offline techniques, while with the transport domain, and the assumption-based Nancy actually does not perform quite well, but once we plug in the actual data, somehow helps the algorithm to perform better.
So Tierney,
Yep.
can you briefly talk about the domain? You say that
Yes.
age value depends on the domain. It varies from domain to domain. So these
Yes.
4 domains somehow look similar, with their age values have similar kind of distribution?
Yes, so as we can see here in this, so as we can see here, the shape of the distribution, do you want me to explain what the problem is of the domain, or what's the heuristic we use?
No, I just want to know that if the age values for these 4 domains have similar distribution.
No, they are not. And so the distribution, this is one example, right? So you can see somehow the common thing is as the heuristic, getting higher and higher, you have your mean of your distribution gonna be higher and higher. Some of the relevance on that, but it's not guaranteed on the distribution of your H star value actually. So for example, let's see, there's a lot of, you can tell the heuristic actually quite lousy for the blocks word when your H value equal 4, meaning when you're getting close to the goal. Your heuristic tells you that you are 4 steps away. Actually, you have to do a lot of moves to get around, to make up to the final configuration of the blocks word. So when it's really depending on the heuristic value and also on the domain itself, right? So okay, hope that resolves it. So that's the results. And then of course we want to somehow see the overhead of plugging this Nancy risk-based approach, will it slow down the algorithm, right? So we want to use the actual time bound, but it's actually very hard because you need a sort of a zero latency operating system, which does this, garbage collections and then all sorts of OS writing and the writing stuff. And then we don't have that. So what we do is we still bounded on the look-ahead expansion limit, but we calculate the CPU time per iteration. Every real-time iteration, we recorded the CPU time. And then for all the iterations, we're using the 95 percentile of all the iterations. So instead of using the max and then the average, we want to use the 95 percentile of all the iterations to see, how for each iteration how fast you can be, right? So here's the 95 on the x-axis, but for this domain there's not a lot of variance across the instances. On the y-axis, it's also still the solution cost, so the lower the better. As you can see, so the first dot would be the 30 look-ahead limit, then 100, then 300, then 1,000. So interestingly, we can see that Nancy is actually slower because while the CPU time says that LSSRTA star can do like 300 expansions, and then Nancy can only do 30 expansions, right? But interesting is even with the 30 expansions, it can already achieve the same solution cost as the 300 look ahead in LSSRTA star. So this tells us that Nancy does incur some overhead in CPU time, but it's worth it to do that because we're gonna spend less expansions to achieve the same performance of the algorithm. All right. And then we have done some following work to compare this to other conventional RL methods, which also take into account uncertainty, right? So we compare to interval estimation, which is very simple yet very powerful. It chooses the top level actions with the lowest lower bound on the 95 confidence interval. So when you have this belief, you back it up, and then you sort them all your top level. You make a decision based on the lowest lower bound on the belief, and that's it. So it doesn't require any risk-based calculations anymore. And also there's Monte Carlo tree search, sampling-based methods. In deterministic domains, people have invented this algorithm called a THTS, trial-based tree search, which is also use some action selection phase using some UCD values to balance between the exploration and exploitation, and then there's initialization phase, and then you have to do some backups, just following the MCTS way to do deterministic search, right? And then we also compare to that. What we can see here is one example in 40 pancake problem. Basically, all the algorithms take uncertainty into account can perform better than the baseline LSSRTA star approach. And then here we can see in this particular case, the Nancy does not perform as good as original assumption-based Nancy, but interestingly, the interval estimation performed quite well here. And then both of them perform better than MCTS, all right? So to summary, the takeaway for this work is distributional methods provide significant improvements compared to conventional offline approach like LSSRTA star, particularly in this online settings real-time search. And then Nancy starts to explore an optimal way of doing online planning. And then our data-driven approach provides an alternative way to implement this framework, and it performs better when the assumption fails. All right. So this work is published in AAA training, and also on the ICAPS workshop on PRL training. And then we are prepared for a GR version for that as well. With that, I'm gonna move on to the second part of the talk, which talk about when to commit to an action in online planning. It's an orthogonal question for online planning. This is a joint work with Shahaf and al. From Bungaria University from Israel, and Aris from Technion, also from Israel, and with Wheeler. So again, we are doing real-time search. For example, if we do thinking of a highway scenario, finding a path and taking the vehicle to the goal, you do a bounded time of search, and then you find the best top level node. Sorry, the line doesn't show pretty well here, but anyway, so here's a line here. here's a dashed line here. And then you find the best top level, best frontier, and then you commit the best top level, what will leading you to the best frontier. And while you moving towards there, you perform another round of search, and then you do commit to the next best level option, so on and so forth, right? So the problem we want to solve here particularly is another meta level problem. Should we commit or not commit a action in your prefix of your current best? So before I show you one extreme of a fixed strategy, basically you do some search and then you commit only one action, right, to the best search frontier. And then there's another extreme which you always commit all towards to your best search frontier, which is included in the original LSCRTA star approach and also Eason's dynamic F-hat approach. And this is what we have in the literature for now. And then the question we want to ask is, can we do better, right? So the limitation of doing this extreme is, for example, it can be too risky to commit all the way to the search frontier because there's a heuristic errors, right? So if you search, this is your best node, and then because the search haven't seen, by just looking at the Euclidean distance, you don't know there's an exit after this, right? There's uncertainties in your values, and then you commit all the way to here, it would be too risky, you would miss this exit here, right? And then if you commit only one, it would be too conservative because you cannot gain too much search time. Ideally, what we want to do is we somehow want to commit those actions are certainly already be the best, right, for us. And then commit all the way to here, and then leaving those still have uncertainties for the next search iterations. And then by doing this, if you commit 3 actions, you gain a longer search time during the next search iteration. So that's sort of the idea we want to try. And then we want to solve. And we propose an algorithm called a flexible action commitment search, which trying to find a principled way to make this meta-level decision. I wouldn't spend too much time on this, but the basic idea is we compute the utility of whether we want to commit for each node along the prefix of your best top level, of your best choice, right? So you have this alpha and alpha, which is the prefix of your best choice in your search tree, and then you compute this utility of what if we commit, what we can gain, what if we don't commit, what we can gain, right? I want to point out here, we're also using a distributional based methods, which trying to evaluate the effect of doing further search or not, which is very, very powerful. Anyway, so once we plug this algorithm into a syntactic domain, here, so it's also a grid path finding problem, but a little bit contrived, so that it has challenge areas for fixed strategies, right? So here, what we can see is the goal achievement time compared to the optimal, the oracle planner, which basically, if you don't do any plan, you already know the optimal plan, and then you're starting to execute. That's our optimal plan. So we show a factor of optimal at the y-axis here, so the lower the better. And as you can see, our facts algorithm can outperform the two baselines, and then also the dynamic F-hat approach, which also using commit all strategy. So the takeaway for this work is, facts start to explore a principled way of doing online action commitment by reasoning about uncertainty. And then it can perform better than the fixed baseline in our grid path finding scenarios. And then if we deliberation on how to allocate search effort carefully, it can benefit online planning.
But you want to put in your mask up a little more.
Oh, sorry. Yeah.
Thanks.
And yeah, and then this work is published to a in-text 21 ICAPS workshop, and then we are preparing to submit this to SOX, and also we're using a similar meta-reasoning technology to solve a SIP planning called a safe interval path planning, which includes some dynamic obstacles in the planning problem, and then we are targeting for each kind. All right, with that, I'm gonna move on to the third part of the talk, which is the last part, talking about bounded cost search using estimates of uncertainty. This is again a joint work with Max and Wheeler. So for bounded cost search, it has this planning problem. You have some initial state, and then you want to find a path to your goal state, right? And then in addition to the planning problem, what you have is a cost bound. So basically the target becomes how can you find a plan that with cost less than the given cost C, right? As quickly as possible. You want to find a solution within the cost bound as quickly as possible. How can we do that? So the state of art before our research is the potential search and the Beast algorithm. For potential search, it's doing just best search on this F linear quantity, which is H over C minus N. It's intuitively what happens in potential search is when you have, so the H estimates how much cost you're gonna get towards to the goal, right? Estimate that. And then this C minus G gives you the budget, the rest of the budget you can have before you reach the goal. So this is the budget, this is what you estimate you will have in your cost, and then this gives you the inverse of the probability of how likely you will have a solution within the bound. And then you just guide the search with that quantity. It performs quite well in practice. But the problem is it does not consider search effort at all, right? So it's just trying to estimate somehow the probability of your question.
How is search effort defined here?
And the search effort so is how much search you're gonna do, how far away, how much further search you have to do. Sort of you have to, for example, in our approach we're using distance to go, right, to estimate how far away you're from the goal, how many expansions you have to do in the future before you reach a goal, right? Sort of, which takes time, right? Okay, and then here's the Beast algorithm, another state of the art, which expand the node among all the nodes that estimate to be within the bound, and then it will expand the node closest to the goal. Among all those nodes estimate to be within the bound, it will expand the one closest to the goal. And then Beast, the problem for Beast is does not consider uncertainty of its estimates, meaning if its estimate a node is barely below the bound, would be the same for a node that is far below the bound. It will treat it as the same. So the algorithm a little bit brittle, because it doesn't have any uncertainty taken into account. So here's our approach. It's called expected effort search. So first of all, we want to estimate, explicitly estimate the probability of finding a solution given a search node, right? What's the probability is your final solution cost would be within the bound. We take the assumption-based Nancy belief distribution. So the mean at the F hat, and then the lower bound at F, and then construct this Gaussian, and then we plug in the cost bound. Then we get this probability mass that you have the cost which is lower than your cost, right? So this orange area will give us a probability value, 0.5, 0.6, 0.9, which tells us how likely the solution cost is gonna be within the bound. And then we also estimate the total search effort. As I mentioned, we're using the distance to go to estimate how much search we're gonna do. And then we do best first search on the quantity of D over P. So it's the expected search effort. Then you just do best first search on that. It will efficiently leading us to a solution that is within the bound. And then the efficiency of the algorithm have been proved in our paper. Can take a look if you want to know more details. Anyway, so here's some empirical results. We run this on, this is a hard problem inverse tile, and then the y-axis shows the CPU time, how quickly you can find a solution. And then the x-axis is the cost bound, the user given cost bound, with respect to the optimal. So 2 means you have a cost bound 2 times the optimal cost. So the larger the value is, the easier the problem is, right? So you can see that all the algorithms can find a solution quicker and quicker if you give a very high budget. And then it's gonna be very challenging if you want the algorithm to find a solution, close to optimal, close to 1. So as we can see, so everything is the lower the better. As we can see, our algorithm access is the best in this particular setting. So we don't include the potential search because it fails to solve instances. so if we include the potential searcher to solve far less instances, so we just don't take it in here. And Beast 95 is a variance of Beast, original Beast, which take into account the uncertainty. We use distribution to guide the search. So yeah, access finds a valid solution faster than the state of the art. And then here's another example in racetrack map using Euclidean heuristic as well. We have a lot of other domains running across a lot of domains in our paper, which is published in High 21. And then we have under reviewed paper, which using the same idea of guiding search by distribution, but we want to solve a bounded suboptimal problem, which meaning you don't know the exact cost bound, but you have input of a factor of optimal. Say we want you return a solution guaranteed within 2 times the optimal. So how can you leverage that idea? So it's under review in AAA 22. So with that, I want to conclude today's talk. The central thesis is we claim heuristic search can benefit from representing uncertainty, and then we show 3 examples in real-time search, concurrent planning and execution, and also bounded cost search. With that, I'm gonna stop here and welcome any question. Thank you.
Questions for our candidate today?
I see some raised hands up there.
Oh, I think
That's
those are
class.
Oh, the class, sorry.
Class.
That's why they showed up, right? I have a question.
Yeah, if you have question online, just unmute yourself and then shout out.
I have a question.
Yeah, yes.
So
Go ahead.
on that last part 3 of the talk, you
Yeah.
said you had 3 assumptions. Did the slide say 3 unrealistic assumptions?
Yes.
What is that supposed to mean?
Yes. so for example, we make assumptions that all your subtrees are independent, right? If you think your search as a graph, it's unrealistic because all the graphs are nested together. You have edges from this subtree across to that subtree sort of thing. But we make assumption that all your subtree is independent subtrees, and then you do more search on this subtree. It's not gonna affect your the value of your value on the other subtrees, sort of. But in practice, it still works even with these assumptions.
Okay.
Yeah.
Yeah, but this is a standard unrealistic assumption.
Yeah.
Reasonable.
Yeah. Yeah.
Standard, not reasonable.
Standard.
Further questions?
I might maybe have a public question.
Yeah.
Can you remind us what was the proposed part of your from your dissertation proposal defense?
Yeah.
And did you do exactly what you promised us last time, or did you deviate? And what was your plan there?
Okay. Yes. So the thing I promised is the second part is the commitment strategy of that. At that time we haven't figured out how to do that exactly yet, and then we implement it and then find it's actually very challenging to do in conventional search domains, like sliding tiles, which I promised to do, and then we find with this Metareasoning overhead, it's actually not gonna improve a lot of the performance. Percent 0.11, improve the algorithm just a little bit, right? So and then we want to show some strong, improvements on the domains. So what we end up doing is a grid path finding problem, but designed carefully on all the, for example, how the baseline algorithm can fail, right? So, and then from there, we do see a large chunk of performance which happens. So here's the what we end up doing is this domain.
Thank you.
Yeah, and then the plan further is make the meta reasoning part even stronger. So we go ahead to another domain called the safe planning, safe interval path planning, which you will have dynamic obstacles moving around in your grid, and then how in that case maybe meta reasoning can be more powerful and then can solve problem better.
Right, but like even in that thing, it's so like the work that you proposed with the adaptation is kind of concluded.
Mm-hmm.
You just have a plan for life after dissertation.
Yes.
Okay, good.
Yeah,
Happy
it's a
to
plan.
hear.
Yeah, we don't.
Nobody's gonna ask a hard question. So, this first part of your talk was about, using data.
Yes.
Using experience.
Yes.
And you're running on random problems.
Yeah.
And you're gathering training data on random problems.
Yeah.
So you're basically like using the answer. So like, it better perform well.
Yeah.
And it mostly does, but not always.
Yes.
So do you have any speculations about, like,
Yeah.
what is it, why does DD Nancy not always like perform as well as regular Nancy? Is there a way we can know if we don't have enough training data? Or are there like still some assumptions that might be tripping us up, like subtree dependence, or like, do you have thoughts about that at all? 'Cause it's kind of annoying. Like, you go to all this trouble to gather all this training data and you're still not always the best. Like, something still like.
Yeah, that's very valid concerns, and then it's a very good question. So the thing we conjecture is, when you're using these assumptions, it smooths the distribution, right? In some problem domains, if that the smoothness of the distribution can actually facilitate the search, it's like canceling out all the noisy arrows, sort of. So if you plug in the assumption-based Nancy, for example, in the normal sliding tile puzzle problem, not the hard one, not the heavier tile or inverse tile, it actually performs quite well, we have to say. So that's sort of the insight in some cases, but we don't have strong evidence to do that, to show you. I'm sorry about that. That's our conjectures on the domain.
Okay, fair enough. Other questions, especially from the general public, that will have to be
If
excused.
you're not asking a question, we kick you out.
Yeah.
You better come up with something.
I have kind of a generic question. So
Yeah.
you said Nancy, and maybe you just misspoke, but you said Nancy's optimal for offline.
Oh no,
What do
that's a
Oh, you misspoke.
yeah.
Okay.
So where Nancy is used to dealing with online, and
Okay.
LSSLT star is also dealing. This all dealing with online settings. We are trying to find a optimal way to solving online problem, and then Nancy starting towards that. It haven't achieved that yet, and we just trying to doing more optimal given the online bounded rationality. Yeah, we don't have any proof that it's already optimal for online.
And so a quick follow-up question. So for Nancy, the big idea is to use the distributions of H over H, right?
Yep.
But as far as I can tell, you don't carry this idea through to the real-time or online planning. Is that right?
Yeah. So that real-time planning, online planning is just a problem setting that that we are interested in dealing because it incurs this time pressure. So which be very challenging if you don't use a distribution to leverage. But yeah, so we are not just some co-authors or some researchers who I meet in the conferences, they also say this can be very powerful for offline as well, maybe for grid research only. So yeah, so it's not limited to online.
Okay.
Yep.
For offline, you don't have time pressure, so why do you care about the distribution? You can follow what A star does, right, and get the optimal solution.
Yeah, so if you don't have the time pressure, yes, but if you are in an suboptimal settings, and then you do greedy search because you want to find a solution fast, right? So in a greedy
But if
search,
it's offline, why do
yeah.
I want it? Why do I want it fast?
Yeah, so many people just, as we thought, they are just misusing the heuristic search technologies. Like in all the ROS planners, they just using offline solvers, pretend that they are online, in online settings, right? So then you're trying to solve the problem as quickly as possible to give you the, so for example, in this anytime setting, you're gonna using a offline techniques to find a full solution, and then once you find the solution, you relax the constraint a little bit, and then find the next solution, so on and so forth. In that settings, for each iteration, you might want to find the solution as quickly as possible. But still introduce some time pressures, implicitly, not explicitly. Yeah.
Is there any member of the general public on the Zoom side that would like to ask a question?
Yep. Yes, I have a question. Have you looked into the case where the node expansions are very expensive, and would this impact your method, or could you somehow modify it via
That's
the evaluation?
Yeah, that's a very good question. So that's why we included those planning domains where. Sorry.
Can someone
Someone accidentally
Accidentally unmuted. Aris is unmuted himself.
Aris, are you talking?
Sorry.
All right.
No, sorry.
Okay.
I
So
think they're great to
yeah,
use the
all right.
bathroom while
So
attending a dissertation.
so for domain-dependent planning, what you do is it takes very long to calculate the heuristic. So for each expansion, you have to calculate the heuristic for the successor nodes, right? So it takes very long to do this. So that's why I think it performs even better in domain-dependent planning using Nancy technologies, I would say. So because since you have this budget, you want to really careful thinking about which expansion you want to do during the search. Yeah.
I have one last question.
Yeah, go ahead.
How you look and how hard you can collect these data for Nancy? So like comparing the two Nancy versions, like the one that you have already assumption for the Gaussian and the one that you need to collect data. So like how hard is collecting data like compared to the whatever you already have? So you don't have time.
So for the original Nancy assumption based, it's very easy because you don't have to collect.
You don't have to collect.
Yeah, you just get it online, right?
Mm-hmm.
So for each expansions, you're looking at your successor's heuristic value, and then looking at the parent's heuristic value, and then compare the edge costs, and then you can calculate the error. And then from there, you collect the global error of your heuristic, and then using that to estimate your distribution. So very cheap. But for the offline, it's sometimes very challenging because you want to calculate the optimal solution for each instances, and then some of the instances are very hard to solve optimally, so it can take a lot longer than the assumption-based Nancy to achieve that. But it's worth it, for example, if you want to launch a company for FedEx to do the deliberation, right? Before you launch the company, you can do a whole huge amount of offline search and then get the correct, accurate distribution data. And then when you launch the company, you're just using the data online for free. So it's also very powerful.
Yeah, maybe a follow-up. Have you looked like how much data you need, or like if you have like small amount of data compared to a large amount, like more?
Yeah, that's a very good question. So I think we did something like that in our GR version, but I cannot have the quite detail. The thing is, for example, if you're representing the distribution using histogram, right? And then there's bins in your histogram, how dense your histogram gonna be, right? We compare it with using 100 bins and then only using 5 bins. Like using less bins is actually not that bad in our in our algorithm. So it's sort of powerful. Yeah.
Great. Thank you.
Yeah. Thanks.
Any other questions? Okay, thank you, Chinyi. The general public is now invited to depart, and the committee members will remain and question the